Well, welcome everyone to today's live stream. Breaking news, new, frightening and really hard to imagine security vulnerabilities, and this time hardware again. And no, it's unfortunately not only Intel, as per the usual recurring theme here. So what is it? Latest stuff here released just this last night or something. RAMBleed, reading bits in memory without accessing them. Certainly never good for security if you read bits and bytes that do not belong to you. It's a side channel attack that enables the attacker to read out physical memory belonging to another process. Never a good thing. The implication of violating arbitrary privilege boundaries are numerous and very conservative based on other software running on the target machine. As an example, in our paper they demonstrate an attack against OpenSSH in which they use RAMBleed to leak 2048-bit RSA keys. Certainly never good if you get access to other people's RSH key. And it can be used for reading other data as well, yeah, obviously. RAMBleed is based on a previous side channel attack called Rawhammer, which enables the attacker to flip bits in memory. That was many years ago, I don't know, 4, 5, 6, 7, way before my YouTube channel here. And I just wanted to give a quick shout out here for you to now to be aware of. Of course, this mostly affects people who run virtual machines, because obviously if you have a account there and run your stuff on a shared system or even virtualization, so of course this could theoretically be used in virtualization and reading your neighbor's guest's virtual machine content. How does this diff even work? And I was surprised when this original Rawhammer, do they write here from when this was? Probably from the citations from maybe 2015 here, apparently. However, I have to say, I think I have run the Rawhammer test system on our AMD Phenom nodes, and I think they were not vulnerable in many hours of running this, so I've not really a huge test set of this myself. So what is it? Rawhammer was, again, 2005, 4 years ago, a side effect of dynamic random access memory in which memory cells leak their charges and interact electrically between themselves, leaking, changing the content of nearby memory rows that were not addressed in the original memory access. How does it work? So this is mostly here in Raleigh Never. So they say different hardware-based techniques exist to prevent the Rawhammer effect from occurring, including recurring support in some processor. Rawhammer, Raleigh, or Never affected DDR2, DDR and DDR2. It affects many DDR3 and DDR4 SD-RAM modules. How does this work? So dynamic memory, for those who do not know, is built up from small capacitors with one transistor here. They write here electrically implemented with one capacitor and one transistor, of course microscopically small, and with millions and billions of them in your memory chips and modules there. And the charge state of the capacitor, charged or discharged, is what determines whether DRAM cell stores 1 or 0 as its binary value. Huge numbers of DRAM are packed into the integrated circuits together with some additional logic that organizes the cell. So this is how this looks, a huge 2D array of your memory with row access and column access. Here are drivers and a sense circuitry here to reading just those memory that you are interested in, just that row. And further organized in matrices, addressed through rows and columns. Memory addresses are applied in a matrix broken down into this, and row and columns address decoders. After the row is selected, the read operation is known as row activation. Reads this bits from the cell like this. Do they have here, which is this? Like one, maybe they have an illustration here. So like probably this one, I guess. So you would select here with row and column select like this row here and read this here into the sense buffer, and here sense amplifiers. And also this is dynamic, so this needs to be refreshed. Obviously the charge in the capacitors do not last forever, so since PC XT and such days, this memory, this DRAM needs to be dynamically refreshed every like 60 nanoseconds or whatever that was, depending on the technology and modules, of course. And so not only is this constantly being read and rewritten, it also is transferring the charge into your sense amplifier if you read this out. So increased density in DRAM have led to physically smaller memory cells capable of storing smaller charges, resulting in lower operational noise margins and increasing the rates of electromagnetic interactions between the memory cells. So obviously if you write here in there, they are so close together, this can just so slightly interfere there with the capacitors that are really tight packed there. And this is how this raw hammer works. The name here from hammering this raws on and on again with the same or similar values, like hundreds or thousand times, to just change the charge. For example, like hammering here the second and the fourth so often with the bit pattern you need until the bit flips here. The charge is manipulated so much that this changes there. As a result, the disturbance error have been observed being caused by cells interfering with each other's operation and manifesting in random charges in the value of bit stored affecting the memory cells, and so on. So this is how this basically works, and so far this was mostly for corrupting the memory. If you have a virtual machine and you want to crash your friends or competing company one, then you, with local access of course, or of course nowadays it can also be just-in-time compiler, right? So it can even be your Firefox, Chrome, just-in-time compiler, raw hammering your data there probably. Again, when this was new, I've quickly run this, didn't found our systems effective, but certainly allegedly to this publication other systems are affected. So what is new? Before this was about manipulating this. By the way, not only crashing, right? You can also certainly manipulate, for example, your process ID or actually user ID there, and escalate your privileges to root, for example, and similar stuff like that. Just raw hammering, determining the address. Of course, this stuff is super complicated. You need to read a lot of memory maps. This is also where on Linux, for example, you usually need your proc file system with memory maps and lay out determine and very specifically determine all the memory addresses to raw hammer the exact address to bit flip your user ID or access. For example, you could even manipulate memory mappings if you raw hammer the operating system's access privilege mapping there in the page tables. You can also widen your access, for example, on system pages and flip this access to write access from read only. So what is new? RAMBleed just released last night or something, reading bits in memory without accessing them. So imagine, so certainly virtual machine or OpenSSH daemon or something, and or even Apache, right? Stealing people's certificate and stuff. So you don't have access to those memory and you want to read it. So raw hammering so often that you create mappings and manipulate mappings, or even just read them. Yeah, reading bits. So yeah, manipulating mappings so that you can read them and similar stuff. And again, is a bug in reliability issues in DRAM, and just like with Intel, smaller, faster, and without the proper, well, some quality assurance. But this is just when everything needs to be cheap and rushed to market and stuff, then just years later, security researchers take too close of a look. So they demonstrate here, just as their cover page advertised, read side channel with OpenSSH 7.9 that extracts an RSH 2048 key from a root level SSH daemon. And the details here are super complex. Not really sure if I should bore you with this. I've only cross-read this. The raw hammer is much easier to understand. The raw RAMBleed is much more difficult because it is again much more about here raw activation page and secrets and sampling page. So apparently this is even more tricky in regards to determining the memory mapping. And by the way, they say here that it also has, because it's like reading, it also can read and sample the values out of ECC memory, because again, this is not even corrupting stuff, this is reading stuff. And and again, this is very specific. In my opinion, this is really amazing that this even works at all, because all the details here are rather fragile, with all the mappings that needs to be studied and analyzed and reverse mapped and memory mapping tricked and memory allocator tricked to lay out your memory very specifically. I would even think after cross-reading this paper, but I'm not yet the greatest expert in this, also not really so much time to spend all day on this kind of studies. But I would think that it should probably be possible to work around this with manipulating the memory allocator of your operating system, not to allow mapping so close to each other. But the challenge is, of course, you want high performance, and usually preventing security vulnerabilities does not go along very well with high performance. So suppose the attacker wants to determine the value of a bit in the victim's secret, like your SSH key. The attacker first templates the computer's memory to find the flippable bits at the same offset in a memory page as the secret bit. For the rest of this discussion, assume the true bit, one that flips from 1 to 0. The attacker then manipulates the memory layout to achieve the arrangement depicted below, like the activation page, secret, unused, sampling page in between the secret. And here each memory row spans 2 memory pages of the size of 4 kilobyte, uses the raw activation page for hammering. The sample page contains the flippable bits, which is initialized to 1, and the secret page contains the secret's victim data that the attacker aims to learn. If the value of the secret bit is 0 and the layout results in a flippable 010 configuration, flippable bits is set to 1 and the bit directly below it are 0, otherwise the secret bit is 1, resulting in a 111 configuration, which is not flippable. Next, the attacker repeatedly accesses the 2 activation pages, which are those activation pages there. I hope, by the way, this is on screen well enough. And she controls the activation page, they controls left, top and bottom rows thereby. So left, top and bottom rows, activation pages here, thereby hammering the middle row being this one here, the sampling page, I guess. Hammering the middle row, because raw mass effects are data dependent, the hammering induces a bit flipping in the sampling page this one, that they are, oh wait a sec, activation page, secret, unused, what? Anyway, something like that, and directly the attacker then accesses the sampling page directly, that the sampling page is this one, checking for bits flip. If the bits has flipped, the attacker deduced that the value of the secret bit is 0, otherwise the attacker deduced that the value is 1. Repeating the procedure with flippable bits at the different offset in the page allows the attacker to recover all of the bits in the victim secret. So sampling page, so they belong together, I would guess. But so the tricky thing is even how to really understand this. I think so they hammer this pages that are mapped so that they belong to the same DRAM row, I guess, otherwise it doesn't make so much sense to me right now. And there you see this, you really need to be very creative to come up with this stuff, and you see you need to very carefully map this. For me, it's just really so surprising and amazing that it's even possible to manipulate your operating system mapping in such a way because you would think it's really difficult to achieve such a layout, that your process maps the pages so in a very specific way that the secret, like the OpenSSH key, is there at the right location for raw hammering and sampling. And so how does it work? Thus we can exploit raw hammer induced timing variations to read data even from ECC memory. And one of the main challenges for mounting RAMBleed and ramhammer based attacks in general is achieving the required data layout. Yeah, just like I just said, layout in memory. Past approaches rely on one or more mechanisms which we now describe. The first particular raw hammer attack relies on the operating system interface, e.g. proc PID, this is the current process ID of your running program, like 1, 2, 3, 4, 5. Page map in Linux to perform virtual to physical address translation, which, by the way, security, maybe this should also just not be allowed for security reasons. Then probably correct me if I'm wrong, how many reasons are there for a valid program to determine the memory map? In my opinion, this is more like for debugging purposes, maybe should not be readable. Anyway, translate for user processes. Later attacks leverage huge pages which give access to large chunks of consecutive physical memory. So huge pages, normally the pages are 4K, but with huge pages On later 386 processors and Power, Spark and such, you can also have 1 megabyte, 4 megabyte, sometimes even gigabyte or terabyte pages for not having too large mapping trees there, page trees. And later attacks leverage huge pages which give access to ERZ, thereby providing sufficient information about the physical addresses to mount an attack. Other attacks utilize memory grooming or message techniques which prepare memory allocators such that the target page is placed in the attacker's chosen physical memory location with a high probability. Again, really voodoo magic that you can achieve this. Of course, this does not universally need, so you need a very deep knowledge of your operating system, certainly, as you even need to read your very specific proc files. This will not work the same way on Linux as Windows. Not even is the interface is different, also the memory allocator is different, so this relies on very specific memory configurations there and mappings. Here are, by the way, defenses. So there are various defenses have been proposed for RAW attacks, aiming to detect ongoing attacks. Again, I would also think, so this is detecting ongoing attacks, multiple papers here, neutralize the effect of being flipped or determined. Also, this can just be avoided with more reliable memory write that is not page bit flippable like this. But also they write here, maybe the problem is maybe I should also in the future use my own PDF software and improve it so that I have a more amazing PDF reader with better note-taking keeps. I wanted to make some notes, but as I'm live streaming from Linux, don't have that here. And so this was it here because I even learned some new things each time I research this kind of stuff, and this is also why I want to summarize this here for YouTube, for this public service feature here of breaking news, because there are multiple things. Let me just quickly check. Access to DRAM bank operates at the resolution of a row, typically consists of 65,536 cells or 8 kilobyte. To activate a row, the memory controller raises the word line for the row. This produces minute currents on the bit lines which depend on the charge in the cells to activate the row. Since amplifiers capture the current at each column and amplify the signal to both copy the logical value of the cell into the latch and refresh the charge, because I think the reading here is destructive, so you need to refresh the charge. Otherwise, if you sample the charge, again, very tiny charges, right, and the very tiny capacitors, so if you sample this charge, it is gone, so you need to refresh the charge of the active row. Data can then be transferred between the CPU and the row buffer, which consists of the latches that store the values of the cells in the active row. Over time, the charge in the cell capacitors in the DRAM leak. So yeah, so they leak to each other, certainly very tiny, like microscopic on the atomic level there, just very small, I don't know, handful of atoms. Correct me if I'm wrong there, but certainly as small as the stuff is, it's not a surprise that this leaks to the next capacitor cells nearby. To prevent data loss through leakage, the charge needs to be refreshed periodically. Refreshing is handled by the memory controller. In old-fashioned PCXT times, this was, by the way, done by the DMA controller directly without any integrated DRAM controller circuitry. That was some DMA channel, I don't know, whatever that was, 3 maybe or something like that, which is why even also on later machines from 286 or something, this was done by a memory controller. Usually software avoided to use the DMA channel that the XT, original IBM XT used for memory refresh. But of course nowadays this is integrated in the highly integrated and high performance memory controller. Certainly you don't want to have this old-fashioned DMA rubbish doing this. And at least once every refresh interval, which is generally 64 milliseconds, yes, it's just that what I guesstimated there earlier in this live stream. For DDR3 and DDR4, LPDDR defines a temperature-dependent adaptation for refresh interval. I did not know this, by the way. First time I read this. The more you read and live stream here, the more you learn. And another thing I learned today is that modern memory controllers use a complex function to map physical address to correct physical location in memory. So yeah, even this is then implementation defines that the mapping might not be fully linear, but interleaved there with banking and channels and whatnot, which makes this whole double-sided, single-sided, one location stuff here even more complicated to determine your bit flipping addresses there in this stuff. And also this certainly goes very well in hand here with caching. Usually this Rawhammer stuff relies on cache flushing and prefetching instructions to achieve this level of bit flipping and bit banging there. Here was some detail I wanted to share that I learned that is somewhere. Again, I wish I could make notes here in this Firefox PDF stuff, but didn't, because here was some in DDR4. There is again, you see how specific this layout is. Again, for me it's a really surprise that you can manufacture it so with the memory mapping that this actually works. I think what I wanted to say is, so again, this is super complicated. You can read this. It makes no sense to read and live stream here this. Even for me it takes quite some concentration to follow all the details with memory templating, placing secrets near flippable bits here with exploiting the Linux body allocator, because so again they also write here Android ion allocator, which is of course not available in Linux, so they also specifically did this with a body allocator storing blocks of equal order in first in last out philo stack like data structure. So this is where you need to do dummy allocations and deallocate and trigger the victim to immediately trigger the victim process, letting it perform memory allocations. When we accomplish this by initiating an SSH connection. Again, so this, in my opinion also, although this sounds very dangerous, as you see, very intricate process of actually achieving this, very specific. So, and you need local, probably most of the time, I guess you need local access, like your own virtual machine running next to your victim's virtual machine, or on the same process, on the same operating system where you have user level process. And I wanted, the one thing I wanted to say, so they have also a little bit de-warning here that it is right now, they have implemented this for DDR3, so they leave DDR4 implementation for further research. Where is what I DDR4? Yeah, maybe somewhere here. So while they demonstrate their attack on systems using DDR3 DRAM, we do not suspect DDR4 to be fundamentally a limitation, assuming that DDR4 memory retains a property that Rawhammer induced bit flips are data dependent, or their techniques for recovering physically sequential blocks depend only on the operating system's memory allocation algorithm and thus are hardware agnostic. However, so they have not done this, so if you run a modern system right now, you are more safe. Of course, those people at Amazon, Microsoft, Google and all the cloud, other infrastructure stuff, they might still run systems from yesteryear with DDR3 and stuff like this. They are immediately affected. Otherwise, DDR4 may be a little bit safe, and also they have not like proven this. Could also be that DDR4 is not as prone to this technique, maybe because they also write here somewhere, so much to not being able to make a note here, that DDR4 has a new feature, which is here. That is also something I didn't knew, which I learned here from this paper, is that DDR4, so hardware mitigations, there are however a few commonly proposed hardware mitigations that have the potential of mitigating RAMBleed, proposed wherein para here, probabilistic advanced row activation, wherein activating a row causes nearby rows to activate with some probability, repeated hammering of an address. So this means repeated hammering of an address, the likelihood that nearby victim rows will be refreshed, as they write here, with some probability. So not always, that would probably cost too much performance, but if you like raw hammer one row like hundreds or thousand times, then eventually the advanced rows could be refreshed just to be on the safe side. I hope vendors implement this rather quickly. And however, those have not been widely adopted, so yeah, please do target. And also, so what I've also didn't know is target row refresh, TRR. Most recent TP LP DDR4, this is low power DDR4 standard, supports ability to refresh a target row with TRR, which after a row is accessed a set number of times, the nearby row are automatically refreshed. So this is similar to that, despite this mitigation already this here cited here already reports ability to induce Rawhammer bit flips on the presence of TRR. So yeah, again, didn't know that target raw refresh existed, but yeah, again, bad news, could maybe also be exploited again. So much to that. Just like with Intel cutting corners there for the latest and greatest performance, and then you just have a little bit of a security nightmare there on your hand. Not amazing. By the way, where do I? There. Anyway, questions on the audience, and yeah, so also there's also is what our recurring theme here is that software gets too complex. Even the Firefox here is not the most amazing and everything, and there you see the theme that the last decade we always had this Moore's law of growing performance here is no longer the case, and on top we get more and more security vulnerabilities in this cloud connected world where everything needs to be hyper secure, like the famous military grade secure, otherwise stuff is hacked, as you see, and you can never make the stuff too secure, because if it's not too secure, eventually security researchers find ways to exploit them, even though when they are super complicated with all the memory layout and operating system memory allocator and hardware specific addressing here of the banks in regards to single and double ranked and sided and stuff and interleaving and so on. That was mentioned probably somewhere like here, yeah, double-sided, single-sided and so on. I hope you learned something. I always find this very interesting to read such papers, even though cross-reading this here for your public service announcement also makes me wonder about a couple of details here that I would need to study another hour or two, but I hope this is already quite some knowledge for you to learn. Also so many details in regards to that DRAM needs refresh and memory addressing even on the operating system level, even that you can get the physical addresses from the page memory page map and such. And yeah, even that if you didn't knew this already, this is why we do this YouTube here for the future, that like stuff like this happens, latest and greatest breaking news, RAMBleed. Yeah, not fun stuff, not nice for all of us who do professional IT, and with all the connectivity, internet, cloud challenges remain at hand. It's certainly not getting easier, especially with so many servers in the cloud and more and more performance getting lost in all the mitigations, not only on the Intel side, but also here raw hammering and DRAM controller upgrades here in the future, and DDR5 hopefully implementing more mitigations for this. I hope you found this interesting. I hope this is probably a good length to keep this here at a reasonable level. Otherwise, if I talk another half an hour, people stop watching it. Anyway, if you want to know more details, if you think, wait a second, there are too many details left open here in this 30 minutes walkthrough, please let me know in the comments. Otherwise, again, I hope it provided a good summary. Let's see what we have. Hello to everyone in the audience. The world will either invent a bigger idiot or a bigger genius, neat stuff, and things have become too complex and full of wired circuits. Now from the video we know that there's another layer of this, and yeah, also this is actually not that complex in some way, but actually this is mostly just becoming too atomically, microscopically tiny. This is just the price for miniaturization, smaller process nodes. Everyone wants a faster Intel and AMD processor and CPU and stuff like this. And then yeah, structures become smaller, leakage becomes greater, the margins for error become smaller, and so on. Everything adds up, multiplies, and yeah, certainly usually it works unless you hammer it enough, then certainly eventually something breaks. Thanks for watching. I hope you find this interesting. As always, leave in the comments what you want to see more summaries, more tinkering, more vintage, more modern. Let me know, and I will probably continue to report. Aside from our weekly IT news summaries that I hope you also find interesting, that I still try to find the right concept for that is efficient for you and me, but also this kind of breaking news that all the sysadmins and cloud infrastructure architects out there should know as soon as possible. Probably makes sense, especially talking about this takes 30 minutes even for the most high level quick summary. Again, thanks for watching, hope you learned something, and I hope to see you soon for all the next videos and live streams to come.